Welcome to The Explainer. Today, we're going to tackle one of the biggest, most fundamental rules in the entire universe. It starts with a number, but believe me, it's so much more than that.
Okay, so let's just jump right in. Why can't anything go faster than light? I mean, it's one of those things we all just kind of accept as fact, right? But the moment you really dig in and ask why, well, that's when you start to uncover something about reality itself that is so weird, so mind-bending, it might just change the way you see, well, everything.
So, you see this number? 299,792,458 meters per second. It's not just the speed of some random particle. No, this number, it's like the universe's source code. It's woven right into the fabric of space and time itself. And to really get our heads around it, we have to start our story somewhere you probably wouldn't expect.
Yep, that's right. Our journey to the ultimate speed limit doesn't start with light at all. It starts with gravity. And it all goes back to a truly brilliant insight from Isaac Newton, who was puzzling over a simple question. Why does the moon stick around? Why doesn't it just fly off into space?
So Newton came up with this incredibly elegant but powerful idea. He said that gravity gets weaker the farther away you are, but in a very specific, predictable way. It's called the inverse square law. Basically, if you double your distance from something, its gravitational pull isn't half as strong. No, it's 4 times weaker. And if you're 3 times farther, it's 9 times weaker. See the pattern?
And here's the genius part. This wasn't just a guess. Newton proved it. He knew that an apple on Earth falls about 16 feet in the first second. Simple enough. Then he did the math. The moon is about 60 times farther from Earth's center than the apple. So, based on his inverse square law, gravity's pull should be 60 squared, or 3,600 times weaker out there. And when he calculated how much the moon falls toward Earth in 1 second, bingo, the numbers matched perfectly. The moon is, in a very real sense, constantly falling, and his law predicted it down to the inch.
So this was huge. It wasn't just some abstract theory anymore. It was a law. And with it, scientists suddenly had this powerful new tool. It was like they'd been given a cosmic clock, a perfect schedule for the heavens. They could predict everything. But you know how it goes. That perfect clock was about to hit a major snag.
Check this out. An astronomer named Ole Romer was watching Jupiter's moons, and he noticed something odd. They weren't sticking to the schedule. According to Newton's perfect clockwork, they should have been orbiting with perfect regularity, but they weren't. Sometimes they'd appear a little early, and sometimes they'd be up to 8 minutes late. Now, in a universe that's supposed to run on perfect, unbreakable laws, 8 minutes is a huge deal.
Now, Romer could have said, well, I guess Newton was wrong. But he had so much confidence in the law of gravity, he came to a much more interesting conclusion. He thought, what if the law is right, but it just takes time for the light to get here? He realized the schedule wasn't off at all. The light from those moons had to travel across space to his telescope. When Jupiter was farther away from us, the light took longer to arrive, so the moons appeared late. And when Jupiter was closer, the light arrived faster, so they seemed early. And boom, just like that, the speed of light was discovered. Not by studying light, but by trusting gravity.
Okay, so we've discovered light has a speed. That's a huge step. But here's where the story takes a turn for the truly weird. Because once scientists started measuring that speed really precisely, they uncovered a property so bizarre, so counterintuitive, it seemed to fly in the face of all common sense.
Let's try a little thought experiment. Imagine you're on a train moving at, say, 100 miles an hour. If you throw a baseball forward at 50 miles an hour, someone standing on the ground sees that ball moving at 150, right? Your speed plus the ball's speed. Makes perfect sense. But what if, instead of a ball, you shine a flashlight? The light zips away from you at the speed of light. But for the person on the ground, it's also moving at the speed of light. Your 100 miles an hour didn't add anything to it. The speeds just don't add up.
This should totally break your brain. I mean, everything we know from our daily lives tells us that speeds add together. It's one of the most basic things we experience. But light just plays by a different set of rules. It doesn't matter if you're standing still or on a rocket ship moving at half the speed of light yourself. You will always measure that light beam moving at the exact same speed. How is that possible?
So what gives? If your speed doesn't add to the speed of light, something has to be wrong. This paradox was a huge stumbling block for physics. And the solution? Well, it came from a young patent clerk who had the audacity to question something nobody else did. He realized everyone was assuming that space and time were these fixed, absolute, unchanging things. What if they weren't?
And that patent clerk, of course, was Albert Einstein. His solution was as elegant as it was revolutionary. He said, okay, let's just accept that the speed of light is constant for everyone. If that's the unbreakable rule, then something else has to give. The universe itself, he proposed, actually conspires to keep light speed constant, and it does it by bending and stretching the two most fundamental things we can imagine, space and time.
So in order to make sure that one cosmic law, the constant speed of light, is never ever broken, the universe adjusts everything else. The faster you move through space, the slower time ticks for you, relative to someone who's standing still. This is called time dilation. And at the same time, the very space in front of you compresses. That's length contraction. Think about that. Space and time aren't this rigid stage the universe plays out on. They're flexible, they're dynamic, and they bend to obey that one single rule.
And this whole flexible space-time thing has a really important consequence. The faster you go, the more the universe seems to push back against you. It gets harder and harder to accelerate. You know that feeling of resistance when you push something heavy? That's inertia. Well, as your speed increases, your inertia, what we call relativistic mass, also increases. The universe is literally making it harder for you to go faster. And if you could get closer and closer to the speed of light, your mass, your inertia, would approach infinity. Now, how much energy would it take to push an object with infinite mass? You guessed it, an infinite amount of energy. And since there isn't an infinite amount of energy in the universe to do that, it's simply impossible. Nothing with mass can ever reach the speed of light. The law isn't just a suggestion, it's physically enforced by the universe itself.
But wait, here's where we get to the deepest, most incredible part of this whole story. This cosmic speed limit, this unbreakable rule, it isn't really about light at all. I know, that sounds crazy, but it's true. Even if light didn't exist, this speed limit would still be there.
So what is it then? That speed, that number, is the speed of causality. It's the maximum speed at which any cause can create an effect. It's built into the very geometry of space-time. You can think of it like a fundamental conversion factor between space and time. Light only travels at this speed because, having no mass, there's nothing holding it back. It's traveling at the universe's natural top speed.
Here's a really cool way to visualize this. Ready? You, right now, are always traveling through space-time at one constant speed, the speed of light. I know, sounds weird. But when you're just sitting still, not moving through space, all of that motion, 100% of it, is happening through the dimension of time. You're rocketing into the future at a rate of 1 second per second.
But the moment you get up and start moving through space, you have to borrow some of that speed. Part of your total motion gets diverted from the time direction into the space direction. So you're essentially trading your speed through time for speed through space. The faster you move through space, the less speed you have left for time, which means time literally slows down for you. That's time dilation in a nutshell.
And please, don't think for a second this is just some weird abstract theory. This is real, measured, and tested reality. In giant particle accelerators, we can see that it takes more and more and more energy to speed up particles as they get closer to the limit. And you know the GPS on your phone? The only reason it works is because the satellites are constantly adjusting for time dilation.
It's like this amazing chain reaction of discovery. Newton figures out gravity by watching the moon fall. Romer then uses that law of gravity to discover the speed of light. And then centuries later, Einstein takes that constant speed of light and uses it as a key to unlock the secrets of space and time itself, each brilliant idea just paving the way for the next one.
So, in the end, it's not just a speed limit. It's so much more. It's the speed of causality. It's the speed of information. You could even say it's the speed at which now travels through the universe. It's the very pace of reality unfolding.
So this ultimate speed limit, it's not just a wall we can't break through. It's a fundamental clue, a signpost pointing toward the deep nature of our universe. Understanding it has already completely redefined our concepts of space and time, which leaves us with a final, fascinating question to think about. If figuring out gravity unlocked the speed of light, what new secrets will the speed of light unlock next?